say that? Okay. All right, let's go ahead and get started, and that'll give me a little extra room and make the people that aren't on time feel guilty. So it's a win-win situation. Okay, thanks for voting me in here. I love getting voted in, except I can never see any of Frank's talks. So, oh well, I guess my transmitting antennas just won't be ready for low solar activity. Okay, I'm Word Silver, N0AX, and I guess you know that, but you selected my talk anyway. So here we go. This is a review of grounding and bonding, and we're going to talk about all sorts of things this morning. I give you an idea of where this came from. I wrote a column in January 2015, I think, called The Myth of RF Ground. And it set off, well, let's politely call it a shitstorm of of comments. If you really want to get electricians excited, ask them a question about grounding and then just sort of sidle off to the side and let them duke it out. It's a lot of fun. There's a lot of perspectives on this. And so in the consequence of dealing with the aftermath and 2 more columns on the subject, it became apparent to me that hams really had a lot of different information. The information that was out there was all distributed all over websites, books, articles, standards, documents, everything. And then there's 800,000 different experts, various versions of the handbooks and standards, and it's very hard to pull it all together. So what I proposed was, hey, how about if I just never mention this again and we're all very happy? And then they said, no, you got to write a book. So I wrote a book about grounding and bonding and tried to pull a bunch of stuff together, had some very capable reviewers and helpers, and so that's basically where this comes out of. The overview of this talk is we're going to talk about what is ground. And everybody knows what ground is, but it's all different. And then same deal. What's bonding mean? What does it mean? It's not some kind of exotic and kinky activity. It actually helps in your ham shack. Well, kinky activities in your ham shack might help too, but in a different way. Okay, AC safety. How does this affect your AC electrical safety? Lightning protection. We're going to go over that. RF management. I don't use the term RF grounding anymore. What we're really talking about is just dealing with the fact that you have strong RF fields to deal with and the currents and voltages that result. And you're just going to manage them. You're not going to get rid of them. You just have to deal with them. Then we're going to talk about ground systems, what they are, how do you put a system together that deals with all these things, and then some resources for you. By the end of the session, you'll be sick and tired of hearing the word grounding and bonding. That's my goal. Okay. And you may understand the difference or more of the difference between ground and bond and the different types of all that. We'll also appreciate the different requirements for all these different types of activity. What are your requirements for AC safety? What are the requirements for lightning protection? And then at RF and audio, and they're all quite different. Then we'll illustrate some techniques as we go so you get some ideas about how to deal with this stuff. And we'll show how a systems approach works to solving all of your problems with one simple solution. No, one consistent approach to the problem will help you solve the requirements, satisfy the requirements for all those different types of grounding. And then I'm going to point you at some more comprehensive resources so you can follow up. And who is this station, who's this talk for? It's for people who are just starting to build their stations. You're just getting started. How do you deal with this grounding and bonding thing? Maybe you're putting up your first tower and you want to make sure that it's grounded and bonded properly so that it's safe. What if you're expanding your station? You know, you're starting out with, like everybody does, you got a table and you got a radio on it, some cables on the floor, and then you got some more cables and some more gadgets and then some more radios and some more antennas. Okay, you're expanding your station. How do you do that properly? What if you live in lightning country? Anybody here from Florida? Okay, or just lightning country in general. Okay, you obviously do something right because you're still alive. Okay. Basically from Seattle. Mark's from Seattle over here, where lightning is so rare that when there's lightning, they write about it in the newspaper and put pictures, and everybody goes, "Ooh, lightning!" And around here, in my station in rural Missouri, I call it the Crawford County Cumulonimbus Discharge Facility, up on up on a hill, and so it takes a shot every once in a while. But if you're worried about lightning, you want to make sure you do stuff right. Okay, and maybe you're just trying for better performance and you're wondering what you can do in your existing station to make things better. This is not for K3LR, W3LPL, KC1XX, N0AX, all these big station guys. They have problems that normal mortals do not have to deal with. You know, we don't have towers that are so big that they create their own electric corona discharge at the top, you know, things like that. So it's for the little pistols and the medium guns. Background references. Here's some good ones. They're all in your book. You don't have to scribble all this down. We have the new book. The NEC handbook is a good thing to know where to get it. It's a massive book. It costs about $200 new. It's about yay thick. You look for the handbook, not the NEC code, the National Electrical Code. You want the National Electrical Code handbook, because that comes with explanations and figures and guidelines, whereas just the code, all it does is state the standard. Okay, these are available at your library. You can get them. You can copy the articles. They call the chapters and stuff articles that apply to you out of them, and then send the book back. Standards and guidelines, the Motorola standard is very good. It's available online. It's for basically VHF and up communication sites. Lots of good guidelines about how to do stuff. The book here, these are the QST articles, Lightning Protection for the Amateur Station, that ran in 2002 by Ron Block. They're available on the ARL website in the Technology Information Services radio frequency topic, then safety. Or if you just Google that, you'll find it. We don't have to actually know anything anymore. We just ask Google. Okay, and then K9YC has these great tutorials on his website. Lots and lots and lots of stuff. Power grounding, bonding, and audio, and RFI ferrites and common mode chokes. All good stuff. This is what they look like. You can see the 2014 handbook is pretty massive. There's a 2017 version. Okay, what is ground? Everybody thinks they know what ground is, but the right answer depends on what you're trying to do. And if you ask me any questions during this, the first two words out of my mouth are going to be, it depends, because everything depends on everything else, and especially when it comes to grounding. So when you say, what's the right way to ground? Well, it depends on what you're asking me. Am I talking about electrical safety? Am I talking about lightning protection? Am I talking about a tower? Am I talking about a station? What? It all depends on the frequency, the voltage, and the current. If you talk to an electrician about AC safety, and he works at 60 hertz, the wavelength is something like 50,000 miles or some ridiculous figure like that. So what it means to be electrically short at 60 hertz is a lot different than what it means to be electrically short at 20 meters, for example. It's greatly different. And then again, up to gigahertz. What about the current? If you're talking about just trying to steer some ground currents for maybe your 100-watt radio, you're talking about orders and orders of magnitude different than what happens when a lightning strike hits your station, and you're dealing with surge currents of thousands. They measure in kilo amps, okay? And that makes me nervous. I don't know about you, but when somebody talks about kilo amps, my hair kind of does that. That's not so good. So you got to know what you're trying to do with the ground connection. Your safety depends on getting that answer right. You want your electrical safety to be taken care of in your station, and your equipment depends on getting all this right. If you're going to hook your stuff up and put those big lightning attractors out there in the field, you want to make sure your equipment is protected. So you want to ground it properly, and your sanity depends on the right answer. Because if you are trying to solve problem A and you apply what goes on for problem B, well, you're going to chase your tail for ages and ages and be frustrated. So it helps to back up and try to understand the big picture. Ground can be a noun, a verb, and an adjective all at the same time. I used to be a datacom systems engineer, which is also known as being an electro-political engineer. And you would hear people having these conversations and using words like protocol and realize that all three of them were having this conversation and using the word protocol to mean completely different things and all nodding vigorously in the up and down direction. And I realized that I'd have to go in and clean up that mess, so I'd go over and get involved. But vocabulary is really important. If you're talking about the noun, ground, well, that's an earth connection. That means dirt, okay? Getting something into the dirt. And it means a local reference potential. Even an op-amp designer trying to handle picoamps of current in his circuit refers to ground. And that's just a local reference potential. That's all it means. It doesn't mean that it's at 0 volts with respect to anything. It just means it's a local reference. And that's what the earth is, even for the big currents. It's just a local reference. When it's a verb, you say, I'm going to ground something, that means to connect to a reference potential. I'm going to connect this point. I'm going to connect this closure. I'm going to connect my back of my transceiver to ground it. When I say ground it, what I mean is connecting it to some identified reference potential. And when it's an adjective, it's a ground conductor or a ground system, that sort of thing. So you need to know the difference, how it's being used. There are fuzzy definitions. You want to stay away from the fuzzy definitions. First thing, RF ground. Ain't no such thing. As I go through my editorial duties in the handbook and the antenna book and QST and all this stuff, every time I see an RF ground, I just get out my red pen and I just scribble it out because it's just a myth. There is no such thing as an RF ground. All you can do is create a reference potential that's about the same. You don't know what the potential actually is, the voltage actually is. All you know is it's going to be the same. You're just trying to make stuff be the same voltage at some RF frequency. Okay, that's all you're trying to do. There's no magic ground anyplace. The other thing is ground loop. So I hear this a lot. You know, the guy's got a buzz or a hum or something or RF feedback. It's always, you hear it all the time. Yeah, you got a ground loop. Well, I'm telling you, ground loops are not as big a problem as you think they are. And there's ground loops at 60 hertz and ground loops at audio and all this kind of stuff. It's just a noise that we make with our mouth when we don't really know what's going on, okay? There are loops. Loops are generally a problem. There are millions of ground loops in our station. Of loops of connectors. Don't worry about it. Just minimize them. They pick up magnetic fields and that sort of thing. All you can do is minimize their effect, but don't think that they're out there lurking in the bushes to give you some kind of a problem with your audio. Single point ground. What does single mean? What does point mean? Well, at 60 hertz, single point could be something the size of a football field, okay? At 20 meters, single point could be something about 1.5 feet in radius. At 2 meters, or maybe up at a gigahertz where the wavelength's about 30 centimeters, single point might be the size of a dime. Okay, so we got quite a range of expectations when somebody says single point ground. Oh, you just connect everything to single point. Well, if they're any kind of distance apart, or even if your ground conductor is significantly long at that frequency, you don't have any such thing as a single point. It's like if I've got a wire and it's 10 feet long at 10 meters, at one end that wire vanishes and at the other end it's a short circuit just because of the way RF works. So when you say single point ground, you got to know exactly what you're talking about, and we're going to get to that. And repeat after me, the earth is not a magic sink into which we can pour RF and lightning and expect it to just go away, okay? It doesn't happen. The earth is not some big 0-volt globe 4,000 miles in radius. It's a surface just like everything else is. So what we want to do is convince the lightning to go into it. We would like to have some safety with the power system, but as far as RF goes, it's just another big thing to flow on, just like your antennas and your wires. Okay, what about bonding? Bonding sounds expensive. It's just a connection between two things intended to keep them at the same voltage. Okay? It's not expensive. You can do it very inexpensively. It sounds hard, but it's not. Okay? It's just a technical word, and when we encounter technical words that we're not really familiar with, well, the sky could be the limit here. Okay, all we're really talking about is a wire that connects a couple of things together. But it does require the right connecting materials and hardware. If it's going to be electrically short, we've been beating that horse for a couple of slides now. It's got to be short and direct. You got to use the right terminals. If you're talking about bonding for lightning protection, where the current might be real high, well, you need to use heavy wire and you need to use the right terminals, and they need to be installed properly. If you're just talking about connecting a couple of pieces of equipment so they're at the same voltage, well, maybe a short piece of number 14 Home Depot wire with a crimp-on terminal on each end would be just fine. Okay, so basically as we go through this, when I talk about bonding, RF bonding, lightning protection, AC safety, we're just talking about connecting things together to keep them at the same voltage. Bonding, wherever you do it, works in your favor for all three requirements: AC safety, lightning protection, and RF management. It helps you deal with all three, as we shall see. For bonding to work, it has to be low impedance, and it has to be short. Remember that 10-foot piece of wire that we talked about? At 10 meters, that's not low Z. If one end of a quarter wavelength piece of wire is connected to a low impedance point, the other end is at a high impedance point. So it might not be low impedance at all. At twice the frequency, it might be low impedance again. So that wire goes through cycles of appearing and disappearing and acting like an inductor and acting like a capacitor, and it has to be really, really short if you're going to ignore it. So it has to be heavy enough to carry the expected current. Okay, if we're talking about lightning, it has to be heavy-duty stuff. Okay, number 6, number 4, number 8, 2-aught, whatever. Big cables to handle an expected current load. Most of our connections in our shacks are not that big. Okay, well, maybe in some of the amplifiers I've seen, but mostly they're much smaller. And you can deal with small strap, piece of number 12, that sort of thing. It's perfectly fine. But once you get outside and you're talking about the environment, it's also got to be real sturdy. When you go and read electrical codes about stuff, and they're telling you number 6, number 8, number 4, and you're going, why is this so big? Well, for one thing, lightning or a serious fault current, the amount of force that can be developed in that wire compared to other wires is enormous, hundreds of pounds per foot. And if you go to YouTube and you Google Coulomb force demonstration, they will show you really big conductors carrying thousands of amps that are close together, and as they start attracting each other and they start resonating and they get closer and closer and closer, we're talking about 2 and 3 inch solid bus bar, and then they hit, and all of a sudden the screen goes white. It's really quite impressive. So when lightning hits that number 10 to your antenna on the roof, it can jerk that wire around. It'll just yank it right out of stuff. You got to secure it to the building, all that kind of stuff. And furthermore, it's got to be sturdy for all the abuse stuff takes outside. You put in your ground bonding wire out to the tower or something like that, and you go, I'll never forget where that wire is. And then next spring, you start digging up a trench for something, and you hook into that wire, and your tower goes, but you got to survive these mechanical insults that wires get. And so number 12 wire, that tractor wouldn't even notice that it cut it. But a number 6 or a number 4 or whatever, it'll at least make you go, what was that? So anyway, it won't yank it off the connection. It won't break your ground system. So you want a heavy-duty mechanical system that will be there when you need it and won't corrode away right away, or it won't get yanked out of its connector. Inside the station, you can use strap, 20-gauge strap, either aluminum or sometimes tinned material, copper, flashing, strap. Strap is the standard, and if you go to any professional communications place, they will tell you solid strap, number 20, is the way to go. Number 14 or heavier wire also works real well. Don't use the braid from old coax. And why is that? Everybody thinks, well, it's a perfectly good braid. Why would it work in coax but not work as a grounding conductor? Well, when it's in coax, it's surrounded by the jacket. The jacket's stretched tight, compressed against that center insulator, and then they put that plastic jacket on it. Okay, that plastic jacket squeezes it, holds it together, and it protects it from water, protects it from oxygen. And those are nice, shiny copper wires when you get them out of the coax. Okay, the minute you take that braid off, you loosen it up. You loosened it up. That's the first problem. And you take the jacket off, oxygen can get to it, water can get to it, chemicals can get to it. And so what happens is all the little wires in there, they start corroding, and they're no longer compressed together. So all those little corroded connections are now your ground connection. That causes RF problems, causes noise problems, all sorts of things. And what you need to do is if you got to use braid because the equipment is vibrating or you got to move it or something like that, use the special heavy flat weave braid that's designed for grounding. Even then, like Frank will tell you, the standard is solid strap. Okay, and braid should never be used where it can get wet. Ever, even the flat weave stuff, because that water will wick up into those connections, and pretty soon you don't have one big solid strap. You got a whole bunch of little wires that may or may not be connected to their neighbors, and that's not a good thing. Somebody asked me, would it be okay to use old coax if I left the jacket on? And I'm thinking, yeah, that would probably work. So as long as but if it's good enough to leave the jacket on, why are you using it as ground cable anyway? So anyway, that could work. Before we go any further, don't be the guy that says, gee, I thought it would never happen to me. I disregarded one time the warning to always disconnect the battery in a Volkswagen before you work on the headlight system, and wound up getting a new Volkswagen. So that's not a good thing. Safety first. Be safe, guys. And when you're wiring stuff, throw the breaker. You know, electricity is a lot faster than you. You know, we're all tempted to reach that terminal and go, you know, to see if it's hot. What the terminal sees is this. Electricity moves a lot faster than you do. Don't let your kids think they can just do the finger swipe. Although everybody knows an old electrician that will walk up and go, yeah, it's 440. Yeah, of course his arm is dead all the way to the shoulder, you know. Okay. And a very friendly reminder from your authority having jurisdiction, local code is the law. It doesn't matter what my book says or what NEC says or R56 or MIL 419. Local code is the law. And the local code is often written so that it takes into account special circumstances in your area, special soil chemistry, special water stuff, things that you have no idea that are out there. Sometimes they just make stuff up, but mostly it's there because of local circumstances. This is what's appropriate for your area. If there is a local code, it's the law. You can live in town where they have an extensive building code, or you can live like I do in rural Missouri. I have a station down there, and down there they have absolutely no codes whatsoever. They have one code. You cannot poop directly into the stream. That's it. And they will write you to a letter to that effect. You can do anything, which is great if you want to put up towers. It's not great if your neighbor wants to open up American Swine Waste and Nuclear Waste Reprocessing Incorporated, but, you know, there's the large print giveth and the small print taketh away. Okay, local code is the law. This is a great book. If you don't know what you're doing, and most of us have a zone in which we're reasonably competent. We can hook up branch circuits and put in outlets and switches and only get shocked a couple of times and all this kind of stuff. Once we get out of our comfort zone, though, it's easy to make some rather serious mistakes pretty quickly. So get yourself a guide. This is a really good guide. It's the one that's out there right now. It's by Cold Spring Publishers. This is on the website. It's in my book. They sell it at Home Depot. It costs about $20. And it's full of really good advice. Lots of pictures, colors, everything, photos. Or, I know this is hard. We're mostly men here, but you might hire someone that knows what they're doing, okay? I'm sorry. I didn't mean to shock anyone, okay? So to speak. See what I did there? Okay. All right. AC safety grounding. Let's talk about AC safety grounding. It has several names, depending on the age of the electrician to whom you are talking. Equipment ground, third wire ground, green wire ground. These are basically the AC safety things to make sure that leakage and fault currents have a path back to this grounding common connection back at your box so that the GFCI or the circuit breaker will blow. Okay, that's what that's for. It's a safety ground. And it also stabilizes the AC power voltage system during faults or transients. If you go out and you look at your power pole, most of them have a butt wrap, they call it. It's just a bare copper wire, comes down, goes into the ground. There's one at every pole or every few poles. And they're at the bottom of the transmission towers. There's also a ground rod at your house. Although Crawford County, God bless them, there was no ground rod at my house. Not a one, just a butt wrap out at the pole. And so I asked the electrician, he said, well, it'd be okay if I put in a couple of ground rods here? He says, can't have too many grounds. Okay. All it does is stabilize the AC power system. So that's the two function of AC grounding, safety and stabilization of the power. So when the lightning hits the lines out there, or Joe Bob drives the boom truck under the lines and causes the line fault, the big transients that come down the line don't get you. They try to stabilize all that with respect to ground. This is what it looks like. If you go open up your circuit breaker box, here's your transformer, here's the butt wrap wire, it goes down to the pole. You've got two phases coming in like this, split phase, two phase, whatever. There's a whole bunch of different names for that. And a neutral wire. Neutral wire comes into this neutral bus where all the white wires from your branch circuits come in. Well, there's also another thing called a grounding bus over here, and that's where all the copper wires connect, or your green wires, or whatever. And the ground bus is connected to the metal of the enclosure, and that's connected to a grounding electrode. It's not just a ground rod, it's an electrode. And there's a jumper. This is called the main bonding jumper, and that connects ground to neutral. And this just gives fault currents a place to go here so that these circuit breakers will open when you have a problem. Okay. There are certain circumstances where this jumper is not required. It's actually counter-required. That means don't do it. And this is spelled out in the NEC handbook for sub-panels. So go look that up if you've got a garage, or you've got an outbuilding, or you've got a second station and you're running it all off of this one service. Go find out what you're supposed to do. Where's your connection between the grounds? Do you run a separate wire? Can you use the cable? Do you put in separate ground rods? Those are special cases. Here we go. And if you do put in those ground electrodes, they shouldn't be less than 6 feet apart. You want to spread them apart so that they have the maximum amount of volume in which they can distribute charge. Okay? You want to bury them, or really get them down close to ground level. How many people have ever shot off a one-shot? Ooh, it's fun, isn't it? It's fun. Yeah, I looked at the video. KF7P has a really nice one-shot video online, and I thought, man, he must have sped that up by a whole bunch. That just didn't look long enough at all. And then I shot one off myself, and it went boom, like that. And all of a sudden it went from 0 to about 8,000 degrees, and molten metal is coming out of this crucible and everything else. It's impressive, okay? So anyway, use it. It makes really nice welded connections. You'll screw up the first one. Trust me, I know this. So be prepared to waste a couple and learn how to do it for about $5 or $6 to $10, depending on how many you buy. They're available from DX Engineering. They're available from your local electrical contractors. They make great ground rod to ground system connections, heavy wires and stuff. If you don't use the one-shots, use the recommended clamps. No hose clamps, no soldering, okay? Use the real stuff. The electricians know what works, they know what can be buried, they know what can be yanked on and have it keep working. These are available at the store. They're not that expensive. This is an Acorn clamp. This is an actual official grounding clamp. Okay, so here's your first challenge. You got your TV antenna on the top of the house. At least that's what your neighbors think it is. Okay, and you've got your required number 10, and it comes down over here. Here's your antenna ground rod. Here's your TV system. The cable guy came in, and he put in a ground rod. And then the telephone guys came in, and they put in a ground rod. And the electricians, unless they're in Crawford County, came in and put in a ground rod. Well, bond them all together. Otherwise, your ground systems all have this big resistor between each one of them called dirt. And we all know dirt, Frank's talking about how to get rid of losses in the dirt, okay, right now. So bond them all together. Tie that all together so your ground system is one ground connection to the earth. Who had a hand up? Yeah. Okay. Seems like everybody has that happen. I don't know what it is. There's some social reason why we put our ham shacks all the way on the other side of the universe from where the service comes in. The nicest thing is to have all of it together, okay? Your electrical service, your cable service, your telephone service, your ham stuff all together, but it doesn't work that way. So what you do is you go around the outside of the house, and every 10, 12 feet, you put in another ground rod, and you take a big piece of number 6 and you bond them all together, and that's called a perimeter ground. You'll see that a couple of times. And if you can't get all the way to the house, around the house, it seems like driveways are a real problem, okay? You can go underneath them, or you can pry out the expansion strip or something, but just go all the way around the house as much as you can. Question in the back. Oh, I thought you were a little twitchy. Okay.
When you put those connectors and a wire in the ground, I almost feel like I need to tape it up or cookie it up or something. But you just leave that exposed to the dirt.
Yeah, all you do he's asking about when you put these clamps on a ground rod and you bury them. Okay, these are specially made so that they stay intact, and it's a special bronze to be put on a ground rod. Now, if you want, you can dig them up every once in a while and check. But when you tighten those suckers down, they're made so that everything expands and contracts thermally together, and they don't work themselves loose. And if you tape them, all you're doing is making sure that any water that gets in there stays in there for as long as possible. Okay, so just use the clamp, put the wire in it, tighten it down, and be happy. Yeah. Yeah. Rebar has another special type of a clamp. Oh, in the concrete, yeah, right. That's a good point. Oofer grounds, slab grounds. If you're going to do that, get somebody that knows what they're doing and has the right hardware for it, because you can't do it after the fact. You got to do it at the beginning. You can't assume that the rebar is all tied together. Use the right clamps. Get somebody that knows what they're doing to make that stub connection out to your ground connection. Thanks for bringing that up. Okay, lightning protection. You can't steer lightning. It doesn't care about you, but you can kind of influence it to try and have it make some good decisions. That's about all you can do. It wants to get to the earth. It wants to get into the dirt, so help it. Okay, give it the best possible path you can to get to the ground. In a lightning protection, because of these pulses, the heavy-duty pulses, very high rise time, high current, the voltage along a conductor, an inductor, is the inductance times the rate of change of current. And when you're talking about kiloamps per second, that means even a little bit of inductance will cause a big voltage between the ends of what you think is a piece of wire. Okay, even a foot of wire with a big current pulse through it has a certain amount of nanohenries of inductance, and it can have hundreds or thousands of volts from end to end, just a piece of wire. Okay, so inductance, that's why you use strap, big flat strap, or big round wire for your lightning protection connections. All the paths should be outside your residence. Don't invite Mr. Lightning inside your residence. Even if you think it'd be a lot cheaper, you could save a bunch of money on running that number 6 through the basement instead of around the outside of the house. You don't want Mr. Lightning in the house. Okay, so all the paths to earth, to the dirt, should be outside your house. And don't make it easy for lightning to go through your house on its way to the earth. Here's a good example. This is a drawing from W8JI's website. Tom has a 300-foot tower on top of a mountain in Georgia. He knows about lightning. Okay, so he says, all right, here's your tower right there, and lightning hits it. Okay, where's Mr. Lightning going to go? Well, here's your single-point ground panel. You did a great job. You got a ground wire out there. And he says, well, that's fine, but you know, there's a really fine ground rod over here. I'm just going to take a shortcut through your radios and all the AC wiring over to this other ground system. That's bad. That's when you get things blown up all the way through the house. And you say, well, I had a ground rod. Yeah, you had more than one ground rod. Okay, so what you want to do is bond them together. Okay, you want to have multiple points of contact into the soil, all tied to a ground rod. Here's your single point panel. Here's one at the tower base. Here's a few on the way over to the service entrance. That's just what you were talking about back there. And so here's lightning. Say it hits the power lines. It comes in. It says, I'm going straight to ground. And oh, look at these fine connections over here. I'm going to go over here. I don't see any reason to go through your shack to get over here when you got this nice big piece of number 6 right here. Give lightning every chance you can to make a good decision in your favor. Help it get to ground without going through the house. And even if you've got the service entrance over here and the ham shack over here, you can build a nice ground system on the outside of the house. Yeah.
Yeah, the tower, like my tower is about 250 feet from my house. You're showing a wire connection from the ground. I have ground rods at the tower.
Yeah.
But I don't have a wire connection.
Okay. This is the bonding. Do I bond to my tower ground system? My tower's way out in the yard someplace. I got ground rods and stuff out there. Here's the house ground system. Do I tie them together? Well, there's 2 answers. For an AC safety point of view, yes, you do. Okay, because that's a very short connection, and you want them both to be at the same potential. Okay, NEC Article 810 or something like that, I'm beginning to sound like an electrician here, allows you to rely on the shields of feed lines to act as a safety ground. Okay, so if you've got RG8, bundle RG8 going out there, and that's tied to your ground system at the tower, then that's okay. That can be your safety ground. Other people say, no, you really need to run a piece of number 6. Okay, and then some people say, well, if it's more than 100 feet, the inductance is too high, it's not going to do you anything for lightning protection. Well, the Army says if it's up to 200 feet, you need to bond. Okay, beyond that, you don't. So this is not settled science. In my opinion, I'd run a piece of number 6. Or if you've got really heavy buried hardline or something, use that. But do bond them together, because you never know. You might run an extension cord out from the house or something like that. And you would really like that ground to be the same potential as the one back at the service entry. So there's safety issues and there's lightning. Okay, tower grounding. Let's talk about tower grounding. Here's how to do it. Here's your tower, okay, and you got your concrete base. Maybe that's part of your ground system or not. It's generally not enough to be the ground system all by itself. So from each leg, or from one leg, you run a short piece of wire to a ground rod, 3 ground rods, and you put a ground ring around them. Okay, and then from there, depending on how much yard you got, how much wire you got, you can run 3 long radials out like this. About 30 feet is what they suggest. Maybe number 4, number 2. I use number 2, 2/0 10 wire. I got a deal on some of it, and that's real good stuff. It welds well. It's easy to connect to the ground system, but whatever you got, whatever you can get from your brother-in-law, right? Okay, run that out. If it's a tower that you use for transmitting, like Frank's talking about, okay, run your radial system out that. Tie that in. The cellular guys, cell phone guys will tell you they get a lot of mileage out of these big radial fields at the base of their monopoles because it helps dissipate that charge into the earth. Give the lightning all the paths it can to get to the earth. And even number 18 is fine. I found a couple deals on spools of number 18 on eBay. So I've got like 10,000 feet of wire in my garage. And whenever I get the urge, I go out and put down some more radials. That'll be just great. Okay, and you can bury the radials or not. You should bury these, your main ones, about maybe 12 inches or so you've got good contact with the dirt. But the radials that work for your antenna field will also help. Bond your feed lines to the tower. The difference between the top of the tower and the bottom of the tower, because of that inductance business we were talking about, can be 100,000 volts or more. So if you've got your coax bonded to, say, a grounded element antenna up at the top, and then you just kind of run it down the tower, down at the bottom, there could be 100,000 volts between your coax and the tower. You think your jacket on the RG8 is going to hold up to 100,000 volts? Well, maybe for a couple of microseconds. That'd be about it. And that's how you get punctured feed lines and all sorts of other things. It's the difference between it's caused by the inductance in the shield causing this big lightning-induced voltage spike. So what you do is you bond them. You get these clamps. These are nice angle iron clamps. They go right onto your tower. They're galvanized so they don't cause corrosion. And they got holes for these little bulkhead connectors. And you can put your PL259s right on them, waterproof them. Another thing you can do if you're using an insulated base tower or something like a vertical and you want to protect that, you can also put spark gaps across insulators. Here's a picture of one of Tom's towers, WAJI. Here's the base. This all sits on ceramic insulators, okay? Well, he wants to protect that, so he just uses a piece of good old copper pipe. That's it, copper pipe. And he puts it close enough to the base so that it's a couple of thousand volts will jump across that gap. All it takes is a piece of pipe or maybe a couple of wires. Just arrange them so that you don't get water or bugs in there to compromise that spark gap. Here's your single point ground panel. All right, when we talk about that, you've got a protected side and you've got an unprotected side. Don't mix the cables. Don't put the protected cables next to the unprotected cables because lightning will jump right across that. Okay, you've got a protected line duplex outlet, and we'll show you what that is. It's a surge protector. Triplite makes them. DX Engineering makes them. You've got coax lightning protectors. You've got your telco lightning protectors. You pound them all on this panel, and you connect that to your ground system, ground rod, perimeter ground system. Everything comes through this panel. You'll learn from experience. Why not make that panel a lot bigger than you think it's going to need to be because you're always adding more stuff, okay? So make it so you don't have to redo it at some point. And then everything you've got, AC, your antenna feed lines, your telco, cable TV, all of it comes here, and then it goes into the house from there. And you also tie in your shack RF ground connection. Ground connection, we're just talking about a short strap from whatever RF management connection you got in the shack over to this ground panel. This is what it looks like. Here's your lightning protectors, the duplex line guy right here, and a rotator. Here's what a single point ground panel looks like in my barn. Electricians will spot several violations right off the bat, but it's in the barn. I figure if it burns down the barn, I'm good, okay? I've got a ground rod down here. I got 2 pieces of flashing, just aluminum roof flashing. They form the big panel. All of my lightning protectors are on a big piece of angle up here. You can see the ground connection, and here's the rotators. This is before I installed all the little gas discharge tubes. And there's one of these out at the base of the tower too. This is a lightning protected remote antenna switch, and I've got little gas discharge tubes here on a terminal strip. And here's the ground panel part, and here's the ground connection, and that goes to the tower ground system, and I clamp that in. Here's K4RO's. His station is right there. It's right above this. So all the cables come down to this thing in his garage, and it's 2 big pieces of aluminum. His switches, his filters, his routing stuff, all this kind of stuff is all on here. And then you can see the big ground wire that goes out to a ground system right there. It says once he did this and stopped having a rat's nest, a big pile of all this stuff upstairs, it says he hadn't had any lightning-induced failures since, and he was having a lot before. Create a lightning protection zone. This is discussed in the Ron Block articles. You identify everything that you want to be protected. It even says clock, okay? And every place that it's got a wire that crosses the boundary, you got to protect it. If you do that and you're good about maintaining that protection, then all this stuff will be protected from lightning. But you've got to have a common grounded connection. You got to bond all your stuff together within your station, and everything crossing the boundary must be protected. Here's how you bond stuff in the shack. I'm going to have to run through the rest of this because we're running out of time. Here's your RF bonding bus. This is a good way to get everything connected together. It's just a piece of pipe or a piece of braid or a piece of strap or a piece of screen behind your equipment, and all of the equipment is connected to it with wires, even the passive stuff like your antenna switch. And then from there, you run a strap to your single point ground panel. That's an easy way to do it. Yeah? Sure, it works fine. It's a nice big fat wire. It's got low inductance. What I do is, you'll see in a minute, is I put a piece of flashing under that for a different reason. But this is a perfectly good way to do it. Okay. Wires and crimp terminals. From each piece of enclosure, I've just got a number 12, that just a little short jumper, and you'll see the picture of it in a second. When you're doing RF management, I'm going to have to run through this real quick to get through the slides. Catch me at the end. Everything in the station is an antenna, and I mean everything. Everything in that picture is going to pick up RF. RF's going to flow on it, and the voltages are going to be different around the station. The current's going to go everywhere. Your job is to make sure that everything is close enough to the same voltage as possible so the current does not want to flow between the pieces of equipment. Okay? Forget about an RF ground. We've already been over that. It's not possible. You're just trying to get everything to the same voltage. Concentrate instead on bonding. Tie everything together, either through a bus or directly from equipment to equipment. All you're trying to do is equalize voltage to minimize current flow. That eliminates hot spots. They're all at the same voltage. There is no hot spot, okay? It reduces RFI from common mode current. Why does common mode current flow? Because the voltage is different over here than it is over there. If you make all the voltages the same, there's no reason for it to flow. And that reduces sensitivity to physical configuration, and you don't have to arrange things on 15 meters differently than you do on 10 meters and all this stuff. We've all had that kind of an issue. And it also minimizes audio buzz and hum, which is important because we're doing a lot of these digital modes with AFSK, and we're using low-level audio signals, so you want those to be clean. Here's how you do it to keep your cables short. Minimize the loop area we talked about before. Use a bonding bus up at the top. You've got all of your short jumpers from the equipment over to the bonding bus, and you run your cables along the bonding bus, and you keep them all together. Yeah, you got to have 3 foot, 6 foot, whatever cables. Keep them all together. Minimize the loop area, and they won't pick up as much junk. Here's responding to your question. Okay, I took a piece of house flashing right here. I bent it over the side of the table. I ran it along the table and screwed it down. It's nothing more than 12-inch aluminum flashing. And basically, you can see my enclosure of this piece of equipment is tied to one of the little screws on this piece of pipe. I just went along with the drill and put in a bunch of sheet metal screws. Make it easy on yourself. And then from here, there's the big strap, and there's my ground cable that goes over to the SPGP. Okay, some good news. One system to rule them all. If you follow these rules, if you think about this as you're laying out your ground system, it will suffice for AC safety, lightning protection, and RF management. You'll solve all three problems by doing one set of things. And remember, all currents flow on all wires. A lightning current isn't going to come down to a junction of wires and say, oh, that's AC safety. I can't flow on that. I'm lightning, so I'm going to go on this one. No, they all go on all the wires. So think about your whole ground system as a complete set of wires that all solve these problems for you. And this is the rule. If you have a single solid ground system made of short, heavy, direct connections, it satisfies all of the requirement. This is what it looks like schematically. This is in your book. No need to squint. And it just shows all of the external ground stuff tied together, bonded to your tower, and everything inside bonded together. Here's your single point ground panel. Here's your AC power panel. Here's another way to do it. Here's your protected outlet on the SPGP, and everything is nicely connected together and bonded together. That's how you do it. Here's your additional resources, bunch of really good stuff. If there's one thing to take away, take a look at this guy's site, www.mikeholt.com. Many tutorials, white papers, examples, NEC handbook illustrations, all sorts of good stuff. And here are the standards. If you really want to put on your big boy pants, these are the documents to get. They're all free, FAA, IEEE, MIL, and you look at them and you go, man, I can't do that. Well, maybe not, but they can show you a good way to do what you can with what you got. Here's your books, WHAI's web pages, all sorts of good stuff, and I think that's about it, and I bet we're out of time. Is this not true? So thanks very much. I'll be outside answering questions. Thanks for your attention.